Today's Tuesday, so what we're going to be doing today is we're going to be talking about waves and the different types of waves. So let's go ahead and get started. As you've seen in the reading assignment, there is two sections of this today. So there's only one with math and the other one is just like information. So let's go ahead and start with here, the properties of waves. Okay, so in here we have some definitions that we need to know. And what a medium is. A median is a physical environment and those through which a disturbance can travel. So that's what a median is. Like, for example, air, water would be a median. A mechanical wave is a wave that is required a medium through which it needs to travel. Sound has to have waves. Like, for example, sound in space would not have a median, so it would not produce a sound. There are different waves types. There is a pulse wave, which is single traveling pulse. And then you have a periodic wave, which has to do with it going one way and then coming back. Sine wave is a simple harmonic motion. Graph of trigonometry function y. Sine x produces this curve when plotted. So it's basically showing you how this wave is at this point here for A. And if you pointed again for B, it would be up at the crest. Then if you pointed it for C, it would be here. And then if you pointed for here, it would be at the trough. Okay? So, displacement. There are two types of waves that you'll need to know. You will need to know what a transfer wave is, and it's a wave which particles vibrate perpendicular to the direction of a wave travel. So when we're talking about transfer wave, we're talking one that has a crest, one that has a trough, and one has an amplitude. Okay, so the crest is the highest point of excuse me, of the wave. The trough is the lowest point of the wave, and the wavelength, which is lambda, is one complete cycle. So if you're doing a wavelength, you can start right here and say, okay, that's the crest, that's the trough, and now it comes and now it comes back up. And at this point, that's one complete wave. Then if you go to up, back down, and back up again, that would make it two. Okay? So that would be the frequency of it, which is the wavelength of lambda. Then you have what's called a longitudinal wave, and a longitudinal wave is like a spring. So instead of it going up and down like this, it kind of goes like that. So it's compressed and then expands. Compressed and expands. The best thing that I think of is I think of a spring and how a spring works. When you're looking at a spring, and I'll give you an example here with my Isaac Newton that I have. So this here is a spring that I have of Isaac Newton. Now, when I'm having this and I'm moving this way through, if I pulse it and you look at it very closely, you will see that there are waves that are close together. Do you see right here where my finger is? There are waves that are far apart, and then I can also have waves that are close together again. So if I let go of this, then this wave is going to travel through here, and that's what it's basically talking about there. It is talking about how that wave is graphed, where you have compressed, stretch, compressed, and stretch. So a longitudinal wave, or particles and mediums, vibrate parallel. So that's the important part, is this is parallel to the direction of the wave is traveling. Sound waves are longitudinal waves because air particles vibrate back and forth in the direction parallel. And then sine curve, it is a dense wave or compressive wave. So if you look, this one here is graph displacement. This one here is graph density. So as it goes through and it has more compression, that's where that goes to. And that's what it's basically talking about there. And then the next thing we're going to talk about is what a period frequency is in speed. So a wave frequency is the number of waves that pass at a given point in time. A period is one complete cycle vibration of a medium particle. And then our speed is going to be V equals F times X, which talks about V, F, and X. So if we have this here, this right here is our formula. But if we have this here, we have 343 meters per second, and our frequency is 262 hertz. The only thing we're going to do is just divide those. So in our calculator, if we take 343 and divide it by 262, we get 1.3991. So I'm going to say this is 1.31 is my answer. Okay? So let's look at the questions that are in the textbook. So the questions in the textbook. Questions in our textbook for question number 1. So we're going to go back. Okay. Yep. It says a piano emits frequency of a range of a low of 28 hertz and a high of 4,200 hertz. Find the range of the wavelength of the air attached by the instrument when the sound wave is 340 megahertz. So what I'm going to do is I'm going to find lambda 1 and lambda 2. We're going to use frequency 1 and frequency 2 because we have 2 here. So we're just taking 340 divided by 28, that's 12. We're going to do 340 divided by 4,200, which is 0.81. Question number 2 says, the speed of electromagnetic wave in empty space is 3.0 times 10 to the meters per second. Calculate the wavelength of electromagnetic wave emitting the following frequency. We have a radio wave that has 88 megahertz. So we're just taking our V divided by F1 to get 3.41. Visible light, 6.0 times 10 to the 8th megahertz. We're doing this divided by this, and that gives us 5.0 times 10 to the negative 7. The last one, X-ray, 3.0 times 10 to the 12th megahertz. And we're just dividing them, and it's all the same thing. Number 3, the red light emanates by an HENE laser has a wavelength of 633 nanometers, and the air travels at 3.0 times 10 meters per second. Well, this time we're looking for frequency. So what we're going to do is we're going to change our formula just a little bit. Where frequency is, we're going to use our V and our lambda to get our frequency. Okay? So then the next section that we're talking about is we're talking about wave interactions. So we can have what's called superposition. And what superposition is the combination of two overlapping waves. So we have a couple of different types of superposition. Okay? We have constructive interference, where you have a wave coming this way, a wave coming that way, and what happens, they combine together, and then when they go opposite, as you can tell, this one here is the same height as that one, and this one is the same height as that one, except they're going in opposite directions. Okay? Then the next one talks about deconstruction interference, when you have a wave coming this way and a wave coming that way, and as they come in, when they come together and join, they do the difference between this and that. But then when they go back, then as you can see, this is still on the bottom, this is still on the top, and they're the same amplitude as they was before. All the instant of two pulses overlap at the instant, They cancel each other out, and were not disturbed at all. Okay, so then it was talking about reflection. All right, this has to do with waves, not light waves. So when we're doing this, say that we have two scenarios. We have one that the string is tied to a pole, and it's able to move up and down. The other one is where it's fixed, and it can't be. It's attached to the wall. And I just wanted to compare the differences between the two of them. When this one goes to the right, to the pole, it moves that energy, and it uses this unfixed rope that's attached. It will actually go up the rope and come back down. And when it comes back down, as you can see, the wave still is on the top. Okay? But when we have this one that's fixed to the wall, the wave goes up, it goes to the wall, and then it comes back down. But look, the wave now is in the bottom section. Okay? A standing wave is a result of a wave pattern that appears that is stationary on the string. So when we're talking about alternative construction and deconstruction waves, when you're looking at that, you have one wave that's going up, one wave that's going down, and it kind of looks like a pattern. And if you look in your textbook to page number 391, it kind of looks like a blur, where it looks like it's just one. And this here is the anode, and you have the node. So when we have the anode, that is a point, the standing wave halfway between the two nodes with the largest displacement. So if I put a line through where the displacement is supposed to be, the highest point here is the anode. A node is where that point standing wave that remains zero displacement. And as you can see, that's them, even though they should be in a straight line. And then the last part that I wanted to talk about today is on page 392, frequency and standing waves. So if we're talking about frequency and standing waves, it gave us an example of just L, okay, and it's just between two sections. But if we have one wave, that's a 2L. If we have this here, this is just L. And then if we have this, this is 2, 3L. Okay? And that's the end of this section. So, I hope that you're learning some things. Like I said, my main goal here is to make sure that I introduce as much material as I can. I am going to go through after you're finished, and I'm going to continue on, I think, for 2 more weeks to finish out the section that we need to get to at the book where I feel like if I was teaching this, this is where I would be. I hope you have a great day, a great Cinco de Mayo day. Miss Bartlett's birthday today, so if you have time to give her a shout out and let her know that you appreciate her. And I want to let you know that I love every single one of you, think of you every day, and I hope you have a blessed day.